Todos têm que saber inglês. Então, bem-vindo ao Instituto de Física Teórica. Este aqui é o ICTP, South American Institute for Fundamental Research. Temos várias atividades. Temos panfletos na mesa quando você sai, se quer pegar para saber mais sobre as coisas que nós fazemos. A palestra hoje vai ser em inglês ou espanhol, mas não em português. Então, talvez se tem perguntas, pode perguntar em espanhol, mas talvez seja mais fácil, porque tem pessoas que não falam nem espanhol nem português, então é melhor ele falar em inglês. Se tem alguma... Então, a palestra vai ser 1 hora, depois vai ter tempo para perguntas. Então, Juan Maldacena está participando numa escola aqui, que está em conjunto com o Dutch... Qual é o nome completo? Dutch Theoretical Physics Research School, alguma coisa assim. Que eles fazem cada ano, mas cada 4 anos eles fazem aqui em São Paulo. Então, estamos fazendo uma escola em conjunto que envolve alunos de doutorado e Juan Maldacena está dando aulas neste mini-curso e ele aceitou o convite também para dar uma palestra de divulgação. Então, acho que todo mundo ouviu falar de Juan Maldacena, ele ganhou vários prêmios. O prêmio que mais me impressionou é o cientista argentino, como que é, do Cronex? Algum prêmio do cientista argentino mais famoso dos últimos 10 anos. Acho que nem tem no Brasil para competir com isso. Acho que não tem esse prêmio aqui. Então, é um grande prazer ter Juan Maldacena aqui, que vai falar sobre black holes and the structure of space-time.
No? So it's a pleasure to be here. So I won't give my talk in Spanish, but I will give it in English with a Spanish accent. Black holes are an interesting... So I'll give first an outline of the talk. So the outline is more or less the following. So we'll be talking about black holes. Black holes were a surprising prediction of general relativity. Almost everyone that thought about black holes, they got some things right and some things wrong. So Einstein thought that they were not physical solutions, they were unphysical, but he was wrong. Chandrasekhar and others showed that they are some avoidable consequence of general relativity. And Hawking showed that they're not even black, so even the name was chosen incorrectly. And we'll see that there can be red black holes, white black holes, etc. And furthermore, he said that they're incompatible with quantum mechanics. And now we have some ideas of string theory. We think that black holes are compatible with quantum mechanics. And by thinking about these problems, we found some relationships between quantum mechanics and the space-time geometry. But there are still many problems that we don't understand about black holes. It might well be that some things that I will be telling about today are also wrong. So, okay, let's, in order to talk about black holes and so on, we have to review some previous things. And this one is the principle of relativity. It's a principle that Galileo first formulated. He said that if you have an observer traveling with constant velocity, then he would observe the same laws of physics as one at rest. So if you are moving in a train, if you don't look outside, you wouldn't be able to notice that you're moving. Okay. So that's the principle of Galilean relativity, and of course he devised this principle in order to argue that the Earth could be rotating and we still would not notice that the Earth is rotating. Now, the principle of special relativity, that's a principle that Einstein introduced. That is the same. The first has 2 parts. The first part is the same as what Galileo discussed, but the second is a statement that there is a maximum velocity for the propagation of signals, and that maximum velocity is the speed of light. So that's a kind of cosmic speed limit. And these 2 things together are a little surprising. So you might be a little surprised by this, because if you have an observer at rest and then you have light that is propagating and you have one moving, your intuition would say that this one should see light going a little more slowly. Okay? Is that what your intuition says? Or no? Okay. I will stay here until everyone says that this is what their intuition says. Okay. So we have someone staying here. He sees light traveling at a certain speed relative to him, right? We have another person here that is moving, and is moving in the same direction as light. Wouldn't he see light going a little more slowly? This is what your intuition from everyday life should tell you, okay? Is that clear? This is everyone's intuition. And it's the correct intuition if you have objects that travel at speed less than the speed of light. So if you had a wave or have sound or whatever, it would be correct. But the idea is that that idea is not correct for light. And the way it manages to be correct is that the time that this observer feels flows a little more slowly. So this observer sees time flowing a little more slowly. So actually, he sees this light traveling at the same speed as the observer who's at rest. So Galileo made the implicit assumption that the time that two observers measure is exactly the same, but Einstein realized that this didn't have to be so, and that the time the moving observer is different than an observer at rest. Now, sometimes one way to illustrate something similar is this idea of the twin paradox. This was pointed out by some other physicists after Einstein. So if you have two twins born at the same time, and one travels very fast and then returns, and so that they meet again, then one of the twins is a little older. Okay? Now, you might say, well, aren't these two twins equivalent? I mean, they just one traveled, but the other one is traveling relative to the first, and so on. Now, the two twins are not completely equivalent, so because one was at rest and didn't feel any acceleration, while the twin that traveled, that started at rest and accelerated and traveled at great speed and then decelerated, that felt some acceleration. So that's what breaks the symmetry between the two twins. Now, let's propose the following little game. So suppose that there is some rule in the universe that the twins are born, and when they meet again, they die, okay? Now, if those were the rules of the game, which twin would you rather be? Would you rather be this twin that stayed with constant velocity or at rest, or this one that was changing velocity? The older, yeah, you would like to be the older one, right? So you prefer to be the one with constant velocity. Now, it turns out that in nature, we have a rule like this, and elementary particles choose to be the older twin. So elementary particles like to live as long as possible, and that's one of the principles that determines the motion of particles. It's the principle of maximum proper time or maximum lifetime, and that is the reason that's how we explain in classical physics that particles in just empty space move along straight lines. By straight line, it means they have constant velocity. So they move along a straight line in space and time. So if we think of space as one of the directions and time as the other, the particle moves along a straight line. So this is the principle of maximal experience life or experience time. Now, so the lessons of this discussion is that space and time form a single entity, and sometimes we use the word space-time. So this sounds like a weird word when you hear it the first time, because it joins two concepts that seem to be different from each other, space and time, but we think of it as a single concept. And time depends on how we move. So depending on how we move, our perception of what is space and what is time is different. And particles in this space and time move along straight lines to maximize their lifetime. Okay, so that's roughly the behavior of matter in flat space when we ignore gravity. And well, there are some more details like quantum mechanics and so on that we'll get into later. Now we go into something slightly different, which is gravity. So Aristotle thought that heavier objects fall faster, and that's also roughly consistent with one's own intuition. But Galileo realized that everything falls in the same way once we remove the effects of the resistance of the air. So now, this fact that everything falls exactly in the same way, so falling the same way means that if you drop, let's say, a very light object, let's say a feather and a cannonball from the Tower of Pisa, both would reach the ground at the same time, if you remove the air. Of course, you would have to make a little tube and remove the air, and then you do this test, and it works. Okay. Now, Einstein then had something he called a happy thought, which is the following. He realized that if you were falling freely together with the, let's say, feather and the cannonball or the rock, you would feel like that gravity disappeared. So you would both be floating and not moving relative to each other. And he called this the equivalence principle. So it's a new law of physics, which says that if you are falling freely, to first approximation, the effects of gravity disappear. If things are very close to you. I mean, if things are slightly more separated from you, there's a little residual force that we call tidal force, but that still remains. But the first approximation, if you have a very small laboratory and you're falling freely, it looks as if gravity disappeared. And of course, we know these pictures of the astronauts and the spaceships all traveling together and floating in space and so on. This is the equivalence principle in action. Now, Einstein combined this equivalence principle together with the principle of relativity, or the idea that, and the principle of a maximum speed of light, of a maximum speed for propagation of light, of signals, into a theory that he called general relativity. And the idea, this general relativity is a theory that describes gravity. And it essentially says that gravity is due to the geometry of space-time. So space-time is not flat, like, let's say, Euclidean space, but it's curved, it has some curvature. And the idea is that a heavy object curves the space around it. The heavy object makes time flow differently in different locations. And then when you have a particle moving in that space-time, it will follow the trajectory of maximal lifetime. Again, it will choose the trajectory in that space-time that where that particle will live the longest. Okay. So we have this picture, and then so. Now, when we say that we have a curved space-time, one of the important things we're saying is that time will flow differently for different observers in a gravitational field. So imagine we have this experiment where or this situation where we have two people, one living in the lower floor of the building. Let's say you live here, and your friend lives here in the upper floor. Okay. Then, if you both have clocks, you would find that the clocks of the person living in the bottom floor would go a little more slowly than the person living in the top floor. I here have greatly exaggerated the effect. So the effect is 1 part in 10 to the 15, so it's a very small effect. But with a really precise clock, you can actually measure this by very tiny difference. In fact, the most precise clocks that people have made can measure a height difference of 3 centimeters. Okay, and this is, again, something that you can test. And, well, as I said, they can test a height difference of 3 centimeters. And it's one of the classic tests of general relativity. So now, if we could have a twin paradox, but now we can have one of the twins could be near a massive body, and that will be slightly younger than the other twin. Okay. Now, what did Schwarzschild do? So Einstein proposed this theory and wrote some equations that the geometry of space-time should obey. And then Schwarzschild solved those equations for the simplest situation that you have a massive spherical body. So some object that is spherically symmetric, so a round object. And Schwarzschild solved for the space-time outside the massive object. Okay? Not inside, but outside. Inside is a slightly more complicated thing because you need to know a little bit more about what the object is made of. But he solved for the equations outside. And he found that a full geometry, so the geometry has 4 dimensions, the 3 dimensions of space and time, and it's curved and so on. But one of the features that this geometry contains is that it tells us how clocks flow, or how time flows at different locations. So if time flows at a certain rate at infinity, as you start approaching the massive body, it flows at a slower rate. Okay? So then if you take the same star, so the full geometry outside depends only on the mass of this, on the total mass of this object. If you make the same object, you make it smaller, keeping the same mass. Well, something happens here. Okay, so you make it a little smaller, then time would run a little slower. So this curve roughly is saying how much time is the rate of flow of time relative to a clock at infinity. So this curve going down means that the time here is going more slowly. Now, if someone was standing here, it will feel some weight, and the weight it feels here is bigger than the weight it would feel when he was standing at this position. Okay? Here we are considering an observer who's standing at a fixed distance from the massive object, right? So it feels some weight, the same as here, we're on the surface of the Earth, we feel some weight, okay? We are, and then the funny feature of this solution was that there was a particular size where this rate of the flow of time was 0. So clocks at this position, sitting at this precise position, would not move. They would just stay stationary. Time would stop. And someone who was standing at this position would feel an infinite weight. Okay? So Einstein thought that this infinite weight was something ridiculous, so therefore this solution must not make sense. Okay? Now, something important about this observers, like this one here, is that it's not an observer that is falling freely. Okay? So this is an observer who needs a rocket or a rope and needs to be, someone has to hold this person there. But what if that observer would fall freely? Now, it turns out that if that person, so this is the same type of diagram, so the white lines are the exterior, so the regions outside that surface where the gravitational force naively is infinite. But if you're falling freely, then you pass this surface, and you don't feel anything special when you're passing this surface. So you move along this surface. You would be traveling very fast when you, you'll be traveling with some velocity when you cross this surface. And you don't feel anything special here. But if you enter this region, inside this region, you encounter a region of the space-time geometry that looks like a mini big crunch. Okay? So it's a part of the geometry that is collapsing. So it's the sphere is shrinking, and eventually that whole space-time region shrinks into a region that is very, very small, what we can call a big crunch. So it's the opposite of a big bang. Okay? So we normally say the universe is expanding, but inside the black hole, the universe is contracting. So we have a mini big crunch inside each black hole. Okay? So at this point, so the fact that you were feeling an infinite force was because an observer who's stationary is accelerating by an infinite amount relative to an observer who's falling freely. Okay? And even if you are in flat space, if you start accelerated by an infinite amount, you also feel a very strong force. Okay? But you would not feel it if you are just falling freely. But once you cross the surface, you cannot come back out. So the singularity is in your future, and you cannot avoid falling into the singularity in the same way that you cannot avoid going into the future. And you cannot come back out to the horizon. Your horizon will be in the past, so you cannot escape the black hole. For the same reason, you cannot travel to the past. Now, an analogy that was made, I think Unruh made this analogy, is that of a river. So if we imagine a river where you have the velocity of water that is becoming more and more rapid as you approach a waterfall. The waterfall would be analogous to the singularity. And then you have some fish in this river. And the fish can travel at some maximal velocity c, which we will call is analogous to the velocity of light. Then if the velocity of the water here is smaller than the velocity at the maximum velocity at which the fish can swim, then the fish can swim upstream and can avoid falling into the waterfall. But if we have a fish, there is a point where the velocity of the water becomes equal to the maximal velocity at which the fish can swim, and then the fish can start swimming here and swimming upstream, and it will always remain in the same position. Okay? That's analogous to time not flowing for the observer who sits at the horizon. And finally, if the velocity of water is faster, then the fish will fall into the singularity. Okay? Now, what's important is that these fish, if the fish cannot look at the, let's say the river, the water is murky, and the fish cannot look at the shore, it doesn't know that, the fish does not know that it's at this position. I mean, the fish is swimming in the water and does not know that he's crossing the horizon. Okay? Does not feel anything special at this position in the river. Now, so a few things were understood. So, and I mentioned some of them already. So we said that the horizon, this surface where time apparently stopped, is actually a reasonable surface in the middle of your space-time for an observer who's falling freely. But once you cross it, you cannot get out. It was further understood that very massive stars can collapse into black holes, and also that there are objects in the sky that look like black holes. So let me just mention a few, these real black holes. So there are two types of black holes. So one relatively smaller type, which are produced by the collapse of massive stars. They produce black holes which are in the range of 10 to 200 kilometers and have masses a few times the mass of the sun to about maybe tens, let's say 60 or so mass of the sun. You can also have very massive black holes at the center of galaxies, and these black holes are very big. They can be the size of the whole solar system, and they can have millions or billions of solar masses. Now, how do you see a black hole? So what happens, I mean, it would be very difficult to see a black hole if there is no matter around, but sometimes there is matter around the black hole, and the matter falls in, and it becomes hot as it falls in and emits some radiation. And that's one method by which we can infer indirectly that there is a black hole. And another is that, a more recent one, is that we can see the gravity waves produced when two black holes collide. And this is a more direct measurement of the black holes. So this is an example of the first case where here, this is a galaxy. So this picture is a very big area in very big size. So there's a galaxy, and at the center of the galaxy, there is the theory that there is a black hole. And what you can see when you look at the center of the galaxy is that there is a big disk of gas and dust and so on that is emitting a lot of radiation. This disk is very big. The black hole here would be about light minutes, or at most light hours. But this disk is much bigger. So there is something here in the center, very tiny, that people think, astrophysicists think, that it's a black hole. And part of this is emitting particles that emit radio waves at very big distances from the galaxy center, and so on. So people think that all galaxies similar to ours have a black hole like this at their center. And there are several radio telescopes today that are trying to look at the black hole that is at the center of the Milky Way. That black hole doesn't have such spectacular signatures as this one. This is called a quasar. But still, there is some emission from this black hole, and people are trying to characterize it. So the second way we see black holes is by the gravity wave. So you have black holes that it can happen that two black holes form near each other, and then they start rotating. And one of the features of Einstein theory is that if you shake space-time, so have some moving matter or moving heavy objects, they can produce vibrations in the fabric of space-time, and this produces waves in the same way that objects are moving on the surface of water produce ordinary water waves. In the same way, these heavy black holes produce these waves. So you need something that is relatively heavy and moves relatively fast in order to produce a large amplitude for these waves. So these black holes produce these waves, and these waves are detected with very sophisticated and sensitive detectors here on the Earth, and they've been detected recently. The first detection was in 2016, and it's one now very interesting field in let's say astrophysics and so on, to detect these gravity waves. Okay, so that's all I will say about the black holes that exist in the real world and experimental aspects of black holes. Now I'm going to turn onto a discussion of interesting theoretical aspects. And black holes are very good to do theory because you don't have to, you avoid falling into them. So we'll have some interesting conceptual aspects. So I'll try to explain what interesting conceptual aspects black holes have. So black holes have some interesting properties. So the first one is their universality. So the final shape of the black hole is independent of how it is formed. And it's only characterized by its mass and its angular rotation velocity and its charge, its electric charge. So you can have, now when you think about stars, stars can have in all kinds of different shapes and forms and chemical compositions. You can have yellow stars, orange stars, blue stars, etc. But if these stars form into a black hole, if they have the same mass, they will form exactly the same black hole. Okay? Well, some might be rotating, but in the end, it's only characterized by these few numbers. And now these are all pictures of the sun, by the way. It's all the same star. Anyway, the point is that the black hole is universal. And it does not depend on what kind of matter formed the black hole. So whether we form it with ordinary matter, a black hole made out of dark matter would be exactly the same. So that's one interesting aspect. Another interesting aspect is that if you collide two black holes, so for example, in that black hole collision that emits gravity waves that we discussed, you form another black hole. And this black hole that you form would have a slightly less mass than these initial black holes, because mass is equal to energy, and some energy got emitted into gravity waves. So we have less energy to make this black hole, so the black hole mass will be slightly smaller. And it's in general a complicated formula. You have to solve some complicated equations in order to figure out what the mass of this final black hole is. And only relatively recently, people have managed to solve these equations on computers. But there is an interesting aspect is that the area of the black hole always increases. So even though the equations are complicated, the equations are such that the area of the black hole is always bigger than the initial areas. This can happen mathematically because the area is proportional to the square of the mass, and so. And this is something that Hawking realized by thinking about the behavior of light rays. So it's an interesting property because the equations are complicated, but one consequence of the equations is simple, can be stated in a simple way. Okay? And it's an inequality. It's not an equality, but an inequality. So we have discussed so far the black holes in Einstein's theory of general relativity, which is a classical theory. And already in this classical theory, they have these interesting properties. But now, once we include quantum mechanics, we find a new surprise. So the laws matter thus obeys the principles of quantum mechanics. So we can have quantum matter, or even the vacuum in our universe is described by so-called quantum field theory. And this theory implies a new surprise for black holes, which is the fact that you can have white black holes. So Hawking realized that the laws of quantum mechanics imply that black holes emit thermal radiation. And this, his formula for the temperature of the black hole is, so the black hole behaves basically as a hot body, some body that is at some temperature. And the temperature is higher the smaller the black hole is. So as you make the black hole smaller, the temperature would be higher. And there is a size where the temperature would be, the black hole would look red. And if you make it slightly smaller, the black hole would look white. The same as if you heat a piece of iron, it would go, as you heat it more and more, it would go from red to white and so on. Now, here I listed the temperatures of black holes of various masses. So if you have a black hole of the mass, roughly of the mass of the sun, which are the types of black holes that form through natural astrophysical processes, these black holes have a very, very tiny temperature. So these are 3 degrees, well, 0.00, many zeros, degrees Kelvin, so degrees above the absolute zero. So this is such a small temperature that it cannot be measured. Okay? I mean, it cannot be measured for a black hole. On the other hand, if you had a black hole roughly of the mass of a continent, it would be very tiny. It would be a black hole of the size of a bacterium. And it would emit mostly white light. And such a black hole would look white. Okay? It would look like a tiny little white dot. So Hawking radiation implies that the black hole can actually look white. Now, why do we have this feature? We have this feature because of something called relativistic quantum mechanics. So relativistic quantum mechanics is the merger of quantum mechanics with special relativity. I won't discuss all the details. All that we will need is that, according to this theory, particles can be created and destroyed. So when you collide particles, you can produce new particles and so on. And according to this theory, the vacuum itself is kind of a complicated object where particles are constantly being created and destroyed. Particles can be created even in the vacuum, but there is a kind of principle that says that energies should always be positive. So when you create a pair of particles, one will have positive energy and the other one negative energy, and energies have to be positive. And so naively, these particles shouldn't exist. However, the idea is that the policeman that ensures that the energy should be positive is constrained by the uncertainty principle. So if you have a negative energy particle that exists for a very, very tiny time, then the policeman cannot check that the energy is actually negative and allows this particle to exist, okay? So you can have negative energy for a short enough time, okay? But after a little while, they should annihilate against the positive energy particle, otherwise we are in trouble, okay? So in flat space, there is no net particle creation because you cannot, I mean, if you start producing particles, they would have to have positive energy, particles that live for a long time, and the energy would not be conserved and would be a problem. So that doesn't happen in flat space. Now, in the presence of a horizon, something interesting happens. So you can have a positive energy particle coming out, and we can have here a negative energy particle, but this would have negative energy relative to, so when we measure an energy, we are always thinking about the time, a particular notion of time. And so the notion of time for the observer outside the horizon and the notion of time for the observer inside the horizon are very, very different. So the flow of time near the black hole horizon is distorted in such a way that the notion of energy changes very drastically. And what the outside observer would think of as a negative energy particle here, from the point of view of the inside observer, this is just a particle with some momentum, some momentum which could be positive or negative, and this, from the point of view of this policeman, the policeman who lives inside, this particle has perfectly nice energy and allows it to exist, okay? And for this reason, due to this distortion of the flow of time, we can have a situation where the particles are created, and the positive energy particle goes to infinity, and the negative energy particle goes into the singularity. And this happens constantly at the black hole horizon, and produces a stream of particles that goes out, and that's this Hawking radiation. So this is a qualitative way to understand Hawking radiation. There is some net particle creation, and the black hole mass, due to all this negative energy that is going in, is going to start becoming smaller and smaller. So as it emits radiation, the black hole will lose mass, and it will have a finite lifetime. Now, these lifetimes are very big for astrophysical black holes. So a black hole of the mass of the sun or the Earth would live much longer than the age of the universe. A black hole with an ordinary mass, let's say we took 100 kilograms and we made it into a little black hole, it would evaporate in a tiny fraction of a second, and so it would be worse than a nuclear bomb. Okay? A black hole of a mass of 10 to the 12 kilograms produced at the beginning of the universe would be evaporating now. Okay? And I picked this particular mass because we don't know of any astrophysical process that could create a black hole with a small mass, smaller than the mass of the sun. But maybe at the early universe, there could have been so-called primordial black holes that were made at the beginning of the Big Bang. If they had this mass, they would be evaporating now. Now, they don't see any black holes. Well, this might or might not exist. None have been detected of this kind. Okay. Also, there could be, in principle, very tiny little black holes that are producing particle accelerators, but they would also decay very quickly. Again, the particle accelerators that have been built have not detected any black hole of this kind. Okay. So Hawking radiation is an interesting effect for black holes. I should mention in passing that Hawking radiation has not been detected for black holes. As I mentioned, this would be very difficult to detect for astrophysical black holes. But there is a very related phenomenon that is related to the creation of the primordial fluctuations in the beginning of the universe. And that is something that hasn't been observed. So there is a related phenomenon in cosmology that is related to the presence of a cosmological horizon. And that effect, closely related to Hawking radiation, has indeed been observed. Or that's at least the interpretation of some observations that have been made. So now I'll discuss some theoretical problems with the black hole temperature. So the fact that black holes have a temperature pose some problems. And I'll try to explain what these problems are. So there are two problems. One is, where does the heat of the black hole come from? And the second is related to the information loss. Now, what is temperature? How do we normally explain temperature in physics? Well, we think that temperature is due to the motion of the macroscopic parts of the macroscopic particles or microscopic objects, elementary objects, that are making a material. So for example, here in this room, we feel the air at a particular temperature because the molecules are bouncing around. So as it gets cooler, they are moving less rapidly than when it's hotter. Okay? That's the only difference between hot and cold air. So heat is basically due to the microscopic motion of the constituents of matter, and that's how we explain temperature in all physical objects. So the question is, how do we explain this temperature in the case of the black hole? What is moving in a black hole that gives rise to the black hole temperature? So associated to this picture of heat as coming from the microscopic motion, there is a notion, thermodynamic notion of so-called entropy. So entropy is roughly the amount of disorder that arises from this motion, or the number of configurations in which you can arrange these constituents so that they look the same at macroscopic sizes. And we have some law of thermodynamics called the first law of thermodynamics that gives us this entropy if we know the energy and the temperature. And so for the black hole, Hawking calculated the temperature of a black hole as a function of the energy or the mass of the black hole. And so you can calculate the entropy using the first law of thermodynamics, and you get that the entropy is equal to the area of the black hole horizon. So you take the horizon surface, you calculate its area, you divide it by the Newton constant and the Planck constant, this combination of constants. Also, there is a speed of light here that I've set to 1. This combination of constants is a particular length scale, 10 to the minus 33 centimeters. It's a very tiny distance. And so if you measure the area, this will give us the entropy. Okay? So that's the number of configurations, or the number of degrees of freedom, or the number of qubits that we need to describe a black hole. Or roughly speaking, the number of bits. It's really qubits because it's a quantum notion, not the classical notion. And this result is very interesting because now we can reinterpret this area law, the fact that the area of the horizon increases, as the second law of thermodynamics. So somehow Einstein's equations, which are classical equations that know nothing about temperature or thermodynamics and so on, somehow know about thermodynamics once we have black holes, once we have horizons and so on. They behave, the solutions of these equations are such that the area grows in the way we would expect it to grow if this area can be interpreted as the entropy of some microscopic system. So there is the question of what are these microscopic constituents of a black hole. And one point is that whatever they are, they should be the microscopic constituents of space-time itself. I mean, black holes are very universal. They don't depend on matter. They arise only from the structure of space-time. You could even make a black hole from gravity waves where there is no matter. And so these microscopic constituents should tell us something about the structure and nature of space-time. Okay? That's why we think this problem is interesting. Now, another related problem is the problem of information loss. So we said that black holes can be formed in very different ways. So we can throw all kinds of information, we can send a lot of information into a black hole. And then it seems to evaporate always in the same way by emitting thermal radiation, which in the first approximation is completely featureless. And now the laws of quantum mechanics do not permit this. So if you form an object in different ways, it has to evolve in different ways in the future. Now, the differences might be very subtle. So, for example, you can burn a piece of paper containing some information, and you can burn it, and out of the radiation coming from burning the piece of paper, in principle, the text that was written in the paper is contained in that information, that radiation that comes out. Of course, in a very complicated way, but it is in principle contained. That's according to the laws of quantum physics. So there should be subtle differences in this outgoing radiation, which would carry the information on how the black hole was made. So the question is, how do you get a description of black holes that where you see this information coming out? So in order to do this, we need a theory that puts together quantum mechanics and gravity. And such a theory has been under development over many years. It's called string theory. So string theory is a theory under construction. I won't discuss exactly what it is. It's a theory of quantum gravity. So it's a theory that talks about the quantum mechanics of space-time. So the theory of Einstein is a theory of gravity that is classical, where space-time is always is a deterministic theory, while a quantum theory of space-time will be a probabilistic theory, where space-time geometry has probabilities of having different shapes and so on. It's a theory that reduces to Einstein's theory under ordinary circumstances. That means at low energies or long distances. And one aspect, and it has many other aspects about the unification of forces and so on that I will not discuss, but one aspect I will discuss is that it can describe in a complete way certain simple universes with negative curvature. So there are some special universes for which we know how to, we think we know how to describe them completely using string theory. And this is done by something called holography, which says that the interior of this negatively curved space-time, so this is a picture of a two-dimensional space with negative curvature. Here, each of these fish has the same proper size, and the fish appear to shrink for the same reason that when you look at the map of the Earth with the typical projection, the region near the poles seem to expand, right? So if you take a two-dimensional space with negative curvature and you project it onto the flat surface of the screen, then you have to shrink these fish that are very far away. Okay? But that's the picture of two-dimensional hyperbolic space. And a negatively curved space-time roughly looks like this. The spatial part looks like this. And then in addition, there is a time direction that you can view it as coming out of the screen. Okay? So that's the situation. And so you can have a gravity theory or a dynamical theory here of gravity here in the interior. and is described by a theory on the boundary of particles that live purely on the boundary, not in the interior, but only on the boundary, that are strongly interacting. So this is a rough picture for the situation. So you could have some object moving in the interior, and then some particles. The same object moving in the interior is described in an alternative way by some particles living here on the boundary. Here I've tried to represent the fact that they are strongly interacting particles by this random motion. The random motion tries to capture the idea that it's a quantum mechanical strongly interacting system. That could describe a classical interior, a classical object in the interior. Now, in the same way that we can describe just some ordinary object, so the idea is that you have an equivalent description in terms of these particles on the boundary or the object in the interior. Now, in the same way that you can think about a bunch of particles, about a small object, you can think about a black hole living in the interior. And a black hole living in the interior is described by a kind of fluid of particles on the boundary. So these are lots and lots of particles on the boundary. Here, this is not an accurate representation because I got tired of putting these particles on the boundary, okay? It should really look more like a fluid or more or less uniform density of these particles. They're all strongly interacting. The idea is that the temperature and entropy of the black hole comes from the temperature and entropy of these particles moving on the boundary, okay? So according to this relationship, the question of what gives heat to the black hole and so on are these particles that are moving but on the boundary of space-time. So we replace both the black hole and the whole space-time around the black hole by some particles that live on the boundary, and the motion of those particles gives rise to the heat of the black hole. So it's a very non-local description. Now, the interesting point is that the theory on the boundary obeys the rules of quantum mechanics. So if you assume this relationship between the bulk and the boundary, so does the black hole in the interior. Okay, so black holes are consistent with quantum mechanics if you assume this relationship. I should have mentioned that this relationship between the interior and the boundary is a conjecture. It's something we believe to be true and for which we have some evidence, a lot of evidence that is true, but we don't know for sure that it is true. Now, I'll try to explain a concept that appears here, which is the idea of an emergent geometry. So the idea that we have some particles that live in one dimension, and then the bulk, the interior, they are describing something that lives in one extra dimension. So I'll try to explain how we can have this higher dimensional geometry from some theory or some system that lives in lower dimensions. And I will explain this by an analogy with words, a verbal analogy. So imagine how we normally think about words and sentences. So let's take a sentence. So this is some sentence. If a man does not keep pace with his companions, perhaps it's because he hears a different grammar. Okay, so that's a random sentence. So we take this sentence, and the sentence is made out of little words. So we can group all the letters into various words. And then we can further group a series of words into little phrases, okay? This is the kind of thing you did in elementary school, right? Grammar analysis. I don't remember how each of these are called, but they have a name and so on. Then various clauses. And there are further some long-range correlations between the words in the sentence. For example, the word man, his, and here are correlated. And also the idea that keeping pace and grammar are also correlated. So we have all these correlations in the sentence. And when we hear the sentence and analyze the sentence in our brain, we are going through all these correlations, we're grouping this, and we're analyzing the depth of this sentence. And the depth of the sentence is, you can think of this extra direction where we do this analysis as an extra dimension, okay? So when we say it's a deep sentence, it means it has, some long size for the extra dimension. Okay, so that's what we do for sentences. But the idea is that in this relationship, the analog of the sentence is the state of the quantum system. So each possible state of the quantum system can be viewed as an arrangement of quantum variables or bits or qubits. And you can think of this as a very long sentence. And the idea is that this bulk space is characterized in the correlations present in the sentence. And in this, and they are analyzing the correlations present in this quantum state. So, and if you have very long distance correlations, they give rise to particles that move inside this background spacetime. So everything that happens in here has something to do with those correlations present in the quantum system. Now, let's ask what is a black hole in this spacetime. Okay, so we go back to this sentence that we were discussing, and now we are going to start changing it randomly. Okay, so we're going to start to change this sentence a little bit. So here, we, for example, changed a few words. So the words that are in different color we have changed. And now the sentence kind of makes sense at short distances and has the same analysis as before. But when we get to a certain level of analysis, we cannot continue. Okay? So here we lost, for example, the correlations between the man, and now it's it and she, and this lecture, and no drummer, and so on. So we lost some correlations, and the sentence makes sense up to a certain level, but there's a kind of horizon. Beyond this level, the sentence does not make sense. Okay? So we lost these longer distance correlations. Now let's say we change it a little more. So we change a few more words. Okay? So here you can read this sentence, and you can analyze it up to a certain level. So you still have some clauses and stuff like this. But we lost the longer scale correlations. So the horizon has grown a little more, okay? We have a horizon closer somehow to the boundary. Now we have some completely random sentence, okay? So random words, the horizon has grown all the way up, okay? Now we have no words, and the black hole is growing. So as we change the sentence randomly, our ignorance grows. The area of the black hole is roughly the ignorance we have of this sentence, so how the amount of nonsense that this sentence has. And the law of increase of area is basically saying that if you start making random changes to a sentence that makes sense, it's likely that you will make it make less sense, okay? And the depth of analysis will have to be lower, okay? Now, imagine that this random set of words was produced by a reversible process, a kind of encryption algorithm, right? So the kind of algorithm that is used to send private information through the internet. So it takes the email you write. Well, emails are not protected like this, but let's say you put a credit card number in your web browser, then the browser applies a process that produces some random letters, sends that through the internet, and so then the thief that would try to get your number would see some random thing like this and would not be able to get your number because the thief would not know how that information was encrypted. Now, the laws of nature are a little bit like an encryption algorithm. Can behave in some cases like an encryption algorithm. Now, it's always the laws of nature are reversible. So when they act on some system, they can complicate the state of the system, but always in a reversible way. So if you run time backwards, you would recover the original state of the system. So recovering the information from a black hole is saying that you have some laws of nature for how this sentence was changed in such a way that you can reverse the process and recover the original sentence. Okay? So the laws of physics on the boundary, they change the state of this boundary theory, but it's analogous to an encryption process. It's completely reversible. And in principle, we can undo the formation of a black hole and recover the original information. Okay, so that's the end of the analogy for now. I'll make now some other point, which is that this relationship, we've been discussing this relationship to use it to learn about black holes, but it can also be used to learn about strongly interacting particles. So we said that these particles were interacting strongly, and so a complicated problem in terms of these interacting particles becomes a simple problem in the interior. So this is another way of somehow getting information out of the black holes, using black holes to solve other problems. And well, this has been used for different problems in high energy physics and condensed matter to gain some intuition about strongly coupled systems. Okay, so now I will continue with this theme of correlation. So in this analogy we discussed, we said that there were correlations between, when we were analyzing the sentence, we talked about correlations, but correlations in a quantum system is what are sometimes called entanglement. So entanglement is a particular form of correlations that can exist in quantum mechanics that is a form of correlation that is a bit stronger than, classical correlations, the kind of correlations you had in the sentence. So the sentence had correlations between words, for example. We discussed some of them. And in quantum mechanics, you have something stronger, which is the property of entanglement. And we'll discuss, in the past few years, it was understood that entanglement plays an important role in building this extra dimension and in building the space-time. And the role it plays is very similar to the one we said for the for the analogy with the sentences. Okay? And I will discuss here one example of a drastic implication of this connection between the entanglement and geometry. And this goes back to the very earliest Schwarzschild solution. So again, the solution for a single black hole. But now we will take, so before when we discussed this solution, we discussed the solution outside a massive object. But now let's consider the black hole solution and put no matter anywhere. So we have a solution which is a solution of the vacuum Einstein equations with no matter, but with spherical symmetry. When you solve that you find the solution that Schwarzschild wrote many years ago. And when you analyze it properly, and it took many years to analyze it properly, when you analyze it properly, you find that that solution is not describing one black hole, but actually two black holes in two separate universes. And the two black holes are connected through the interior. This is a kind of picture of what the solution looks like. The solution is a full space-time, it's four-dimensional. But here we're only drawing a two-dimensional slice, let's say a two-dimensional part of the solution. Everywhere on this diagram there is a two-dimensional sphere. The vertical direction is roughly time, and the horizontal direction is roughly the radial direction, or the distance from the black hole. And these diagrams are such that light propagates at 45 degrees. So here is the presence of the horizon. So if you have light coming out of the horizon is a light-like surface, so it's a surface where light would somehow be stopped. Here it would be like the fish that was swimming at the same velocity of water, right? So that's light coming out of the horizon. It's stuck on the horizon. And that's roughly the picture. And so what's important here is that this region here far away is essentially it's flat space. It looks like flat space. And the horizon looks like, well, the horizon of two separate black holes. So we have here, this is like the exterior of one of the black holes. This is similar to the pictures we were drawing before for the geometry of the Schwarzschild solution. And we have a similar one here on the left, a flat space region far away, and then a black hole horizon. And these two black holes are somehow joined through a common interior. They share a common interior. So that's just a solution of general relativity. And we can have a solution which is closely related to this one, which is one where we have two black holes very separated in space. So we have one black hole here and another black hole, let's say, in another galaxy. And there's a solution where they are joined through the interior exactly in the same way as these two solutions we discussed before. The Schwarzschild solution was joined through the interior. Now, if you find two black holes in nature produced by gravitational collapse, they will not be described by this geometry, okay? Because there they would have some extra matter in the interior. They would not be solutions of vacuum Einstein equations. All that I'm saying here is that you could, in principle, have this solution, okay? I haven't told you how to make the solution. I'm only saying that this is a possible solution of the equations, okay? Now, one attitude is to say, okay, I ignore the solution. I don't like it. It's too weird, okay? But that was said about the black hole, too, that it was too weird. I don't like it. The question is whether this solution has some interpretation or arises in some physical process, some physical situation. Now, this solution is sometimes called a wormhole, but it's not a standard science fiction wormhole. It's called a wormhole because this blue surface, this looks like the surface in three-dimensional space, and then so here the pink surface is roughly this blue surface here. So here you have one of the black holes, and if you travel, well, you cannot physically travel, but if you imagine following this surface, it will lead you all the way to the black hole horizon, and then if you continue, then you come out of this black hole horizon, right? A bit like a wormhole connecting two distant visions of space-time. But it's important that if you travel along here, you are not following, you are traveling faster than the speed of light, right? So if in this geometry, if you travel faster than the speed of light, you can go between one side and the other. But if you travel at speeds which are less than the speed of light, then you have to travel, let's say, in this direction at the line which is an angle less than 45 degrees from the vertical. And so if you make that travel, you come in here, and you end up at the singularity. You enter this interior, and the interior is a big crunch. You end up at the singularity before you can escape to the other side. So it's a wormhole, but it's a wormhole that is dynamical and that is shrinking as time progresses. Okay? So the wormhole exists at one point in time and then shrinks as time progresses. Now, this type of wormholes are consistent with the laws of physics as we know them. So in fact, they are a solution of Einstein's theory. Einstein's theory, we think, is a correct description of nature. So they are consistent with the laws of physics as we know them. We had said before that if we had a black hole, so we can think of the black hole as a system, as a quantum system that is described by a set of microstates, by a set of quantum states, as least as seen from the outside. And so the idea is that in the complete theory, this kind of wormholes would be viewed as two quantum systems that are correlated. They are entangled. And entangled is a particular correlation in quantum mechanics. And that this geometric connection comes from this entanglement. Okay? So if you have two distant systems and they become entangled, or you make them in such a way that they are entangled, they will have some geometric connection through the interior. So let me go back just to explain this, again to the analogy with the sentences. So an analogy would be the following. So imagine we had the same sentence we had before, and we somehow analyzed the sentence. And here we have the similar sentence, but in a different language. Okay? Here I wrote it in Spanish. So then when you analyze this other sentence, the particular letters are different. But the general structure, when you reach to a certain level, the structure of the sentence and the meaning is the same. So up to a certain depth of analysis, so you can start analyzing the sentence, and at a certain depth of analysis, the two join into a single common meaning. Okay? And that's a connection that exists between the two sentences that is in the space of meaning and analysis. Okay? And the idea is that, again, space-time is some kind of analysis of quantum systems, and when two quantum systems are entangled, they have some common features, and that generates a geometric connection. And just to explain in a different way the physical meaning of the geometric connection, let me say it with a story. So imagine the following story. So we have two people, let's call them Romeo and Juliet, and they like each other, but their families don't like each other. And so they forbid them from meeting, they prevent them from meeting. Sometime in the future, they keep Romeo here in this galaxy, and they send Juliet to Andromeda galaxy. But these people are very resourceful, and they manage to exchange a bunch of entangled qubits, and they manage to build two black holes that are perfectly correlated and entangled. They are very, very powerful, and they have powerful quantum computers and so on. And after they are done, they generate two black holes, one here, Romeo's side, and the other one very far away on Juliet's side. Okay? And now, after they create them, they jump into the black holes. Let's first look at the bottom picture. And they just jump into the black hole. And their families see them jumping into a black hole, and they say, oh, they committed suicide by jumping into a black hole. Okay? And that's what the writer of the story also said. But on the other hand, if you look at the full spacetime geometry, what happens is different. When Romeo and Juliet jump in, they actually meet in the interior. Okay? Just a short time after they jump in, they meet in this interior. In this version of the story, they die at the singularity. Okay? Now, there are other versions of the story that are a little more complicated, where they manage not to die at the singularity. And they use a concept called quantum teleportation and so on. I won't discuss that today. There are still many questions, and perhaps one of the most important questions is the better understanding of the black hole interior. So we had the equivalence principle that tells us that there is no problem when we cross the horizon. And we don't know how to describe the interior geometry using the same variables that we use to make manifest the outside observer. So we don't have a right analogy similar to this verbal analogy that we use to describe the interior. Okay. And those are some of the mysteries. That's one of the main mysteries that really remains to be solved for black holes. And it's a very important one. It's a very important mystery, because if you manage to solve it properly, then you would understand big crunch singularities. And if you understand properly big crunch singularities, then maybe you can reverse time and understand Big Bang singularities. And then hopefully we'll understand how to describe the Big Bang in our universe. And that's one of the main motivations for studying black holes, is to really understand this singularity in the interior of the black hole, which is a system that we think can be understood perhaps more easily than the Big Bang singularity, which is the one we would really like to describe for describing the beginning of the universe. So in conclusions, black holes are fascinating objects where the geometry of space-time is deformed in a dramatic way. Black holes and quantum mechanics give rise to interesting theoretical challenges. And string theory can describe black holes in a consistent way, at least from the outside. And space-time, in this picture, space-time is an effective or approximate concept which arises from more elementary particles living on the boundary of space-time. And I mentioned that entanglement or quantum correlations are very important for determining the structure of space-time. Okay, thank you.
Okay, so we can have questions in English or Spanish or Portuguese. We can translate. So let me just, before I forget, people that are leaving, if they want to sign up a list so they can get information on our activities, there's a list outside. Tem uma folha de papel se você quer deixar seu nome e e-mail. Who wants to start?
Hi. How can we theoretically measure the electric charge of a black hole?
Well, as you measure the electric charge of any other object, right? You put another charge and see what the force it's making on the other charges.
Yes, because we cannot get closer to a black hole, so.
Yeah, but if you have a black hole and there is some charged particle moving around it, you would be able to see what its electric charge is. I should emphasize that for black holes that are made in nature, the electric charge is close to zero, because they are made essentially from neutral matter, so the electric charge will be zero. But in principle, theoretically, they could have a non-zero electric charge.
Mm-hmm. Okay.
More interesting also is that they could also have a magnetic charge. And,
yeah. And can radio telescopes detect the Hawking radiation from a black hole?
No. The Hawking radiation is very, very tiny, very tiny temperature, and it's smaller than the temperature of matter around it. It's even smaller than the temperature of, let's say, empty space around it, because empty space with no matter still has the cosmic microwave background radiation, and the cosmic microwave background radiation is at 3 Kelvin, at 3 degrees, and this was at many zeros below that. So a black hole that is made in nature would have cosmic even if it has no matter and so on, it would have cosmic microwave background radiation falling in. Now, if you wait for many times the age of our current universe, presumably the cosmic microwave background radiation, well, the cosmic microwave background radiation will go down, right? So if we wait to a time, let's say 10 or 100 times the age of our current universe, then you would, at least these black holes would start emitting radiation rather than absorbing radiation.
And my next question is, let me see here. Why do antiparticles do not fall into a black hole when generating, while generating particles and antiparticles in the horizon of the horizon event of a black hole? Because in the black hole, which has an event of horizon, you said that there are particles and antiparticles generation. Yeah, and the antiparticles fall into the black hole, but the particle does not. Why?
Yes. Well, if you go back to what I said, I never mentioned the word antiparticle, just to avoid this confusion. So, for example, a black hole would emit positrons and electrons in the same rate, but there would be positive energy electrons and positive energy positrons, okay? The negative energy particle is the one that goes in, right? So I made the distinction between positive and negative energy, not between particle and antiparticle.
Sorry. Yeah. Thank you.
No problem. Yeah.
Hi. Good evening, Mr. Maldacena.
Yeah.
There have been other theories proposing the emergent spacetime picture recently, namely quantum triangulation and so on. And one of the most recent examples is comes from the field of Grassmannians by Nima Armani Hackett, and it proposes that spacetime actually arises from a structure called amplitohedron, and just as well as particles and field interactions. Do you see any connections between the developments in Grassmannians and the duality picture of quantum gravity?
I don't yet see a direct connection, but certainly those studies are studies of, they share the following aspects. So you send in things from infinity, and then you try to determine what comes out, right? Just from some general principles and some geometry, and there is the geometry of the amplitohedron. Yeah, but it's a description that is perturbative, and we don't know how to make a non-perturbative, so some description that would be exact as these descriptions that we're talking about here. But I think there is probably some connection between the two things. I mean, they're not they're not in different universes, if you wish. They're the same theoretical space. They're probably different aspects of the same thing. Or, yeah.
So is there any hope of extending the lessons learned from the ADS-K to the case of spacetime with zero or positive cosmological constants?
Yes, there is hope, but now one way to say it is that we only have to reverse a sign. We need to go from negative to positive cosmological constant. And so, of course, the case of positive cosmological constant is more interesting. I would like more to have, it would be wonderful to have a theory sort of similar like this and so on for positive cosmological constant. That case is physically more interesting because our universe is more similar to one with positive cosmological constant than one with negative cosmological constant. we are only studying the negative one because we can, not because it's more interesting than positive cosmological constant. So far, there hasn't been a lot of success in understanding the positive case. There are some examples, but for very weird theories of gravity, and maybe the right lessons haven't been extracted, or we need some new theory, and or it is in general a little difficult to generate examples of this duality of having a particular universe corresponding to a particular theory. And many of the examples have used some special symmetries that are present only in these cases with negative cosmological constants, such as supersymmetry. But we don't think that that's essential, and hopefully the future will understand whether the other version also makes sense.
Good evening, Professor. I would like to ask something about the issue of negative energy in Hawking radiation. Why is the negative energy forbidden in this case if it does exist in classical mechanics? In which sense is negative energy a problem?
Okay, so in quantum field theory, energy, well, it so happens that in quantum field theory, energy has to be always positive, and is always positive. Why does it have to be always positive? So let me see. So in certain cases, well, there are different ways to understand this positivity. One is to start from the basic rules of quantum field theory, and you derive that it should be positive. The energy that should be positive is a so-called null energy, an integrated null energy, so some special notion of energy. And in some cases, it's related to some aspects of quantum information theory that tell you that it should be positive. But I don't have a very simple explanation. It's it's roughly speaking related to the fact that the vacuum is minimizing this energy. And so then any fluctuation or deviation from the vacuum has to have positive energy.
Thank you.
Yeah.
Professor, do you think we will prove the conjecture, the ADS-CFT? Is it really important to prove, or we can equally well apply and obtain good results, and etc.?
Yeah, I think it's important to prove it. I think with our current understanding of string theory, it's impossible to prove it because one of the sides, the interior, is not defined completely. Now, string theory is defined as a kind of perturbation theory where you start with free strings and then interacting strings and so on. A lot of progress was made understanding the free strings. So how free strings are represented in the gravity, how free strings are represented in the gauge in the boundary theory. So boundary theory, you have particles that carry color, and carry a special kind of. Let me just say that the particles on the boundary form little chains, and these little chains of interacting particles have behave as if they were strings. And the world expert in this subject is Pedro Vieira here, and he was the one who did the calculation showing that those strings made out of gluons behave like fundamental strings. And it's a beautiful subject, and it's the best test we have of the relationship. But you could still entertain the possibility that perhaps for more complicated things like black holes and so on, and if you want to go to all the details of the microstates, it fails for some subtle reason so that we haven't understood yet. So that's still a theoretical possibility.
Do you think that the graviton particle is like hidden in the fifth dimension?
That the
graviton, the graviton.
Well, the graviton is, right. Let's go back to the verbal analogy, right? What was a particle in the bulk? Was a correlation between words in the sentence, right? So the graviton is a particular kind of correlation between words, between the quantum state in the system. That is a kind of correlation that is produced by taking the vacuum of the particles here on the boundary and making a small change in the boundary metric, so sort of heating it a little bit, making a little dent in the shape of the geometry, and that produces particles on the boundary that spread out and produces a certain correlations between the particles on the boundary, and that's a graviton. That object is a graviton in the bulk. Maybe this description was too abstract, but it's the accurate description.
Thank you.
Yeah.
So, Professor,
yeah.
When you talked about how the information contained in a bounded region of space-time, and correct me if I'm wrong, is fully contained in a boundary,
yeah.
That reminded me of how in multivariable calculus you can use things like Green's theorem or Stokes' theorem and such
yes,
to
yes.
know things about bounded region subsets of Rn, which is as far as I studied, by only looking at their boundaries.
Yes, yes.
Is there a deeper or maybe even trivial connection there, or is this just a coincidence?
It's different because the connection between bulk and boundary is more non-linear, if you wish, more complicated. But yeah, in spirit it's similar. As a very rough spirit is similar, but in detail it's different. Actually, optical holography is more similar to what you are talking about. So optical holography is an optical hologram is a two-dimensional photographic plate that encodes a three-dimensional image. So when you illuminate it, let's say in the simplest case, when you illuminate it with a laser with monochromatic light, you can see a three-dimensional image. Okay? I mean, there are more sophisticated ways to make it work with natural light too. And so there you store the three-dimensional information in a two-dimensional surface. But the whole way you reconstruct the wavefronts and so on is just it's linear theory, so it can be understood simply and explicitly. And it was understood simply and explicitly by Gabor and so on, who invented holography. The optical holography. This is different because the construction of the space-time involves the strong interactions of the particles on the boundary. It seems to be a crucial feature. And so the map is not explicit. But we would love to have something as explicit as what you are saying. So like proving, so I was asked before whether we can prove it. So proving it is to find a relationship like that going between the boundary theories and the bulk theory. So if you could find something similar to the Green's theorem or whatever, that Green's function that given some boundary values, you get the interior, something like that would be proving it. But yeah, we don't have something explicit. We think they are the same, and we can do calculations in both sides and show that they are the same, but it's not an explicit relationship. Finding an explicit relation like the one you are talking about would be proving it.
Thank you.
More questions?
Does the ADS-FT correspondence need string theory, or can I define the correspondence without string theory or even without supersymmetry?
Yeah, the idea is that it should hold in more general cases. We don't know that there are more general cases of completely well-defined theories of gravity. So if you want a really well-defined example, the only examples where both sides are defined independently are through string theory, the only known examples. But there are some examples which are rather similar. They don't define a recognizable theory of gravity in the interior that people have been proposing and studying recently. Some examples that are based on systems similar to condensed matter systems. that have some features of gravity, many features of gravity. And they are quite exciting because, and it's a current of topic. Actually, I'm giving lectures about this in this school. They have the promise of perhaps realizing some of these ideas in simplified settings in a lab and so on. So you don't need very complicated systems, you need relatively simple systems. And then you don't get the full Einstein theory of gravity, but you get some theory which has some aspects of Einstein's theory of gravity, some interesting aspects.
Okay, so let's thank Juan Maldacena for what a wonderful lecture. É só para repetir.